Okay, Herculean task is really the term. Well, I'm always very happy to sing Sundar's praises, but this talk is rather very difficult for me to give for many reasons. So I'll come to that by and by. So let me first begin with yes, what? Okay, so let me first begin with a very brief academic biography of Sundar. So he did his BSc in mathematics from Madras Christian College in 71 and masters from IIT Madras in 73, and then he went to the US for his PhD, where he worked at Indiana University, and that is a picture of his very famous thesis advisor. Most mathematicians will recognize it, Paul Halmos, and his thesis is titled Characterization Theorem for Integral Operators. Now, since then, so let's see, he has authored 1, 2, 3, 4, 5, 6 books, 69 papers, and directed 6 doctoral theses. And this is the volume of work that I am expected to cover in about an hour. Now, if you see very carefully, if you look very carefully at that slide, there is a little dot after Halmos' photograph, and that's supposed to be a full stop. Sundar is a real stickler for punctuation and capitalization and all such matters, so I didn't want to be guilty of omitting that full stop over there. Not in the sense of being a pedant, but more for the reader's sake, to make things as easy as possible for someone who wishes to read the work. And if you notice carefully, there's no full stop here. It's directed 6 doctoral theses, and that's because it's going to be followed so far. There's lots more to come. Okay. So much of Sundar's work deals with Hilbert space and its surroundings. So I want to explain something about Hilbert space. Oh, by the way, so I should say why it is difficult to, why this talk is difficult for me to give. 3 reasons. First of all, one is the large volume of work I already mentioned. Second is the audience is very heterogeneous, so it's hard to please everybody. And finally, my own limitations. I'm not an expert. He has worked in many areas, and I'm not an expert on most of them. So I'll try to do the best that I can. But most of Sundar's work, in any case, revolves around Hilbert space. Hilbert space is named after the mathematician David Hilbert. He was the leading mathematician of the late 19th and early 20th centuries. I want to give some idea of what Hilbert space is, so this part is going to be extremely elementary. So let's begin with one-dimensional Hilbert space. One-dimensional Hilbert space is just a line. You can just think of it as a number line, which you see in probably elementary school. It has numbers. Every point on it corresponds to a number. So a single number denotes, represents a point on that number line. Going up the dimensions, we have 2-dimensional Hilbert space. That's the plane, coordinate plane, where we do analytic geometry. And there, every point is represented now by a pair of numbers. And if you go still further, we have 3-dimensional Hilbert space, where every point is represented by a triple of numbers. Now we could go down dimension by dimension, but our geometric intuition sort of gives up at this point. We live in a world of 3 dimensions, and it's hard to imagine spaces of higher dimensions, at least for me geometrically. But we can, on the other hand, look at this side, number, pair of numbers, triple of numbers, and of course we can extend it to whatever we want. Now instead of going dimension by dimension, so in one fell swoop, let's go to the infinite dimensional version of this. So infinite dimensional version of this is what is called Hilbert space, normally denoted with that calligraphic H. And here, as you would expect, a point in Hilbert space is not represented by 1, 2, or 3 numbers. It's represented by a whole infinite sequence of numbers. Now, it's represented by an infinite sequence of numbers, but when dealing with infinities, we have to be careful. So these numbers have to satisfy some conditions, and that I've written in the small print over there, which I won't explain. And here, the numbers that we are normally used to dealing with are real numbers, but in Hilbert space, the nice Hilbert spaces, always we have complex numbers as coordinates. And that there is a picture of David Hilbert. Okay, so we have Hilbert space. This is the object. And in mathematics, we have objects, and the other interest is what kind of maps or transformations we have between these objects. So for Hilbert space, the correct notion is something called a bounded operator on Hilbert space. So again, I'll give you a very simple example of bounded operator on Hilbert space. I'll consider two-dimensional Hilbert space, which is the familiar plane, and consider a bounded operator on this. So let us consider on a two-dimensional plane the operation of rotation around the origin by some angle. So you take some angle, fixed angle theta, and rotate every point around the origin by this angle theta. So every point gets taken to a new point, and we could ask what are the relations between the coordinates of the point originally and the point finally. And again, some analytic geometry will show you that the relationship between the old and new coordinates is given by a matrix equation. So these here are the new coordinates, and those are the old coordinates. So this represents a point in this two-dimensional Hilbert space. This represents a point or a vector in two-dimensional Hilbert space, and this matrix represents some kind of operation that you do on the old one to get the new one. So this is a simple example of a bounded operator on two-dimensional Hilbert space. Now of course you would imagine that when the dimension of the Hilbert space becomes larger, one would deal with larger and larger matrices, and of course for infinite dimensional Hilbert space, then the matrices that you will deal with are of infinite size. So similarly, certain matrices of infinite size represent bounded operators on H, and the certain again is in the fine print. The certain is because we need Hilbert space is not all sequences, only a certain subset of sequences, and so operators we want, the nicely behaved operators are not all but only one small subset of all these matrices. Now these operators on Hilbert space, you can add them, you can multiply them, and they form an algebra denoted L of H. So the study of L of H is central. L of H and various subsets of it is central in mathematics. Now there are three areas of mathematics that deal with this. So one is called operator theory, another is called matrix theory, and the third is operator algebras. These are very closely allied, but nevertheless distinct areas. They have, their flavor is different, but all we can say have something to do with this problem of trying to understand operators on Hilbert space. Now Sundar has worked in all these three areas, and so I want more or less the way I have written it is the chronological order. Initially he worked in operator theory. His guru Halmos was an operator theorist, and then later he has several contributions to matrix theory, and most recently in the last say 25 years he has been working with operator algebras. So I want to begin with this. So now I'll begin with operator theory. So now the kid gloves are off. So that's all the, now I'm going to plunge right in. Okay. So I want to start with Sundar's thesis. So Sundar's thesis deals with the so-called integral operators on Hilbert space. So let's begin with this. So let X mu be a separable probability space and H be L2 of X. Now if you recall that symbol script H which I wrote earlier represented one particular Hilbert space of sequences, and here I am using the same symbol for something that looks quite different, something which I am calling L2 of X, but doesn't matter. Essentially these are the same object as long as X is sufficiently complicated. It's the same Hilbert space as earlier. So we have this Hilbert space, and there are some definitions which are needed. So two kinds of definitions. So two definitions we need. One is that of a bounded kernel, and another is that of a Karleman kernel. So a bounded kernel is a measurable function on X cross X, satisfying the condition that a certain operator, so this operator that I am calling A, you can think of it as a kind of rotation if you wish, acts now on elements of the Hilbert space. Elements of this Hilbert space are somewhat like functions. So it takes a function and then gives you another function as the output. And this is said to be a bounded kernel if this thing defines a bounded operator. Bounded operator in the sense of the definition that I did not make. And further, it is said to be a Karleman kernel if some finiteness condition is satisfied, and the finiteness condition being the finiteness of a certain integral associated to this function k. So we have the relevant concepts here are separable probability space, bounded kernel, Karleman kernel, and their associated operators. So these are the terms that I will need in order to go further. Now this is a picture that most people will recognize. This is a picture of John von Neumann. I think one of the, at least the foremost, I think, intellectual giant of the 20th century. He worked in lots of areas: mathematics, physics, computer science, economics, game theory, and whatever he touched, he transformed. So our interest in von Neumann is this theorem that he proved in 1935. So what von Neumann proved in 1935 was for when an operator on Hilbert space is essentially the same as a Kármán operator on L2x. Okay, so this I'll read it out and then try to explain things. So the theorem is this. So if X is a not purely atomic measure space, an operator on a separable Hilbert space is unitarily equivalent to a Kármán operator on L2x if and only if 0 is in its right essential spectrum. So what is this supposed to mean? So first let me see what is this unitarily equivalent. Unitarily equivalent for operators means essentially the same as. So as far as Hilbert spaces are concerned, it's the same. That's what unitarily equivalent means. So this theorem is trying to tell you when an operator on a Hilbert space is roughly the same as a Kármán operator on L2x. And von Neumann gives this condition, that is, this number 0 is in a set called the right essential spectrum of that operator. So Sundar's thesis generalizes this theorem. Okay. So what he proved in his thesis is the following. Again, under the same conditions on X, X is not any measure space, but with a very mild condition that it's not a purely atomic measure space. If X is a not purely atomic measure space, then So an operator is unitarily equivalent to an integral operator on L2x if and only if 0 is in its right essential spectrum. Now if you compare this with the theorem of von Neumann I wrote earlier, you will see that the condition is for both is the same, that is 0 is in the right essential spectrum. And here the conclusion is this is equivalent to something being equivalent to an integral operator, and there it was something equivalent to a unitarily equivalent to a Kármán operator. So a special case, so therefore this what Sundar's theorem therefore implies is that any integral operator on L2x for x of this kind is actually unitarily equivalent to a Kármán operator. And I'll just mention a few words about how Sundar proves this theorem. So associated to this measure space X, so we said there is a Hilbert space L2x, but there are also a whole host of other spaces called the LP spaces. These are not Hilbert spaces, but certain generalizations of them. So these are, sorry?
Finite mu.
Oh yeah, associate, x mu being a probability measure. So associated to x mu are a whole set of Banach spaces LP of x, and there is a natural inclusion mapping from L2 into L1 when mu is a finite measure. And so Sundar's observation is the following, his theorem. So if A is an integral operator on L2x, then the induced operator I circle A going from L2x to L1 is a compact operator. What this means is that if you take an operator, so this is something from L2x to L2x, and then regard it as going from L2 into L1, then this thing is that thing is the induced operator. The induced operator is a compact operator. So it gives you this condition must be satisfied for A to be an integral operator. And this, using this together with some very pleasant arguments, essentially will prove this theorem about 0 being in the right essential spectrum. Okay. One more contribution in operator theory is Sundar's book with Halmos, and not the date, it's 1978, that's just an year after his PhD thesis. I'm sure there are very few mathematicians who can say they are the author of a book within a year of their PhD thesis. And let me tell you what the reviewer of this book has to say about this. The style of the book is lucid, lively and entertaining, as we have come to expect from the senior author being Halmos. Now, but now if you read Sundar's work, if you follow Sundar's work over the past several years, this remark applies just as well to all of Sundar's writings as well. Lucid, lively and entertaining. I'm sure many of you who have been following his blogs and his newspaper articles will definitely attest to this, at least the non-mathematical part, but it's equally true of his mathematical work. Okay, so that I've concluded with the part on operator theory. So now let me next move to his results in matrix theory. So for his results on matrix theory, I have chosen as an example a paper that he wrote with Bapat in 1985, which deals with majorization. So here are some definitions. So a matrix is said to be a doubly stochastic matrix if all its entries are non-negative real numbers, all its row sums are 1, and all its column sums are 1. So it's a matrix, and when you add along a row and you add along any column, you get 1. This is a doubly stochastic matrix. Of course, such a matrix necessarily is a square matrix, because you can add all the entries of the matrix, and if you add along the rows you will get the number of rows, if you add along the columns you will get the number of columns. So such a matrix is necessarily a square matrix. Now examples of doubly stochastic matrices are the permutation matrices. These are matrices, square matrices, which have exactly a single one in each row and each column, the rest of the entries being 0. Okay, so this is the result of Berkoff and von Neumann. Berkoff proved it initially, and his proof was rather long, and von Neumann came along and gave a much simplified proof. It's now called the Berkoff-von Neumann theorem, and this says that every doubly stochastic matrix is a convex linear combination of permutation matrices. Now I'm not going to explain what convex linear combination means. It roughly means, suppose you take 3 points, convex linear combination of 3 points is every point which lies in the triangle that they form. Or if you take 4 points in space, you can take the tetrahedron that they form, and every point in the tetrahedron is a convex linear combination of the 4 vertices. So in some sense, Berkoff-von Neumann theorem tells you what are the extreme points of the set of all doubly stochastic matrices. Now one corollary of this, oh, by the way, I should say for this part of the talk, I have shamelessly plagiarized from a talk that Sundar gave last week here on majorization. So I have taken all this material from there. The Berkoff-von Neumann theorem implies the following. If you take 2 vectors alpha and beta in Rn, this just means alpha is an n-tuple of real numbers, beta is an n-tuple of real numbers, then beta can be expressed as d times a for a doubly stochastic matrix D, if and only if beta is a convex linear combination of various rearrangements of alpha. So alpha is just a set of numbers, alpha 1, alpha 2 up to alpha n. You can take all possible rearrangements of these numbers, each one gives you a vector, and then take convex linear combinations of this. The set that you get is exactly the set that you get by multiplying alpha with all possible doubly stochastic matrices. Okay, so now let me come to majorization as such. Okay, now one little more notation is needed. You take any real numbers alpha 1 up to alpha n and arrange them in decreasing order. When you arrange them in decreasing orders, may not be strictly decreasing, weakly decreasing order, denote that vector by alpha down arrow. So alpha down arrow denotes a rearrangement of alpha as a decreasing sequence. And these 3 pictures will also be more generally familiar. So this is Hardy, G.H. Hardy, Littlewood and Polya. So Hardy, Littlewood and Polya, at least according to what Sundar said, proved the following theorem. So what they proved is that if you take alpha and beta in Rn, two conditions are equivalent. One is that the condition that we discussed earlier, that beta can be expressed as d times a for a doubly stochastic matrix D. And the second condition is a set of inequalities. This is a set of inequalities among the betas, and involving the betas on one side, the alphas on the other side. There are n of them, and the last one is not really an inequality, it is an equality. There are n minus 1 inequalities, and 1, the sum of the betas should be equal to the sum of the alphas. These are conditions which are necessary and sufficient for beta to be of the form dA. This is due to Hardy, Littlewood and Polya, and this leads to a definition. A good theorem will lead to a good definition. And this, so if the equivalent conditions above hold, then beta is said to be majorized by alpha. So to say that beta is majorized by alpha tells you something about like beta is less than alpha in some sense, and the precise sense in which beta is less than alpha is expressed by these equations. Of course, now you are comparing sets of numbers. So I mean, how do you say one set is less than another set of numbers? If it's just a pair of real numbers, you could compare, but when you are dealing with sets, there are many notions of less, and this is one such notion, and that's called majorization. So beta is said to be majorized by alpha. Okay, so what Bapat and Sundar showed in 85 is the following theorem. I'll state it first and try to explain some of the terms involved. So they begin with a function phi. This goes from MNC. MNC denotes all matrices of size n cross n with complex numbers, as with entries complex numbers. So take a map from MNC to MNC, which is of a specific kind being unital, trace preserving, completely positive map. Doesn't matter what that means. It's a certain kind of map from MNC to MNC. and then you take any positive matrix. There is a notion of positivity for matrices. Take any positive matrix, then and associate it to any matrix. In fact, there is a set called the spectrum. The spectrum of phi A is majorized by that of A. This is their theorem. Okay. So what this is saying is, in some sense, when you apply this mapping, completely positive, unital, trace preserving mapping to any positive matrix, what you get has in some sense a smaller spectrum than that of A. The spectrum decreases in a very, very well defined manner in the sense of majorization. Okay. So one should ask, why should one prove something like this? That's always a good question to ask. But before that, let me tell you what is a unital, trace preserving and completely positive map. So it's a theorem attributed to many people, maybe to Choi, to Krauss, and to various people, I think, that a trace preserving unital completely positive map of M and C has this form. It's of a specific form. You take a collection of matrices and define phi of A to be the sum of Vi star A Vi, where Vi is this finite collection of matrices satisfying some conditions. So this is a very nice characterization. You see this nice characterization, you go from something totally general, this kind of definition, to something very, very concrete. So it gives you a very concrete representation for maps of that kind. So this is a unital trace preserving completely positive map. So why did Bapat and Sundar do this? So one reason is the following. They showed the following. A very special case of this theorem applies when phi of A is A sure product B. If A and B are two matrices, now there is a standard way you multiply matrices, and which we all learn, and there is also the simple minded way of multiplying matrices. You just multiply term by term. If you have two square matrices of the same size, you could just multiply them term by term. That is the simplest way of multiplying, and that is called the sure product. It also turns out to be important in some contexts. And in this context, if phi of A is A sure B, where B is a positive matrix with diagonal entries 1, then this phi A is an example of a unital trace preserving completely positive map. And then a variant of this theorem, not quite this theorem, but a variant of this, they established a stronger form of a conjecture due to Marshall and Olkin. So let me not get into that. That is the application that they made of this result. This was in 85. But rather interestingly, now we have a new branch of science called quantum information theory, which deals with information and how you transmit it across quantum channels, and what does it mean to have good codings in the quantum sense, and various kinds of questions. So this subject stands at the intersection of mathematics, physics, and computer science. So in quantum information theory, there is a notion of something called a quantum channel. And a quantum channel is exactly the same thing as a unital trace preserving completely positive map. So that is what is the definition of a quantum channel. So what they proved much long ago is some result about quantum channels. So it conceivably has applications to quantum information theory. So what they have shown is when you take this operator A and pass it through a quantum channel, something decreases in some well defined sense. In the sense of majorization, the spectrum decreases. Okay. Yeah. So with that I will move from majorization to the third aspect of Sundar's work, and that is operator algebras, and that is what he has been working for quite a long time now. So again, the subject of operator algebras began with von Neumann. Well, not quite. He certainly made very, very significant contributions. So in the 30s and 40s, von Neumann and his collaborators Murray and others wrote a series of papers called rings of operators. There's rings of operators 1, 2, 3, 4, a whole series of papers, and in which this concept of what they call rings of operators, what we now call von Neumann algebras, is developed in great detail. So let me just define what a von Neumann algebra is. So we begin with a Hilbert space H, and then we take all bounded operators on H. That's what we said. They are the objects of interest, and this forms an algebra. And this algebra has other structures. It's what is called a star algebra. There is a notion of a star operation that you can do on this algebra. And a von Neumann algebra is a star subalgebra of this L of H. So it is a smaller object than this one, consists of certain elements of L of H, and satisfying some condition, and this condition is phrased as an analytic condition here. It's closed in the topology of pointwise convergence. So one of the initial things that von Neumann proved was that this is equivalent to a totally completely algebraic condition on such an algebra of operators, and that is his famous double commutant theorem. But let me not get into that. Okay, so this is a von Neumann algebra, and and here is Sundar's book on one-Neumann algebras. It's called An Invitation to One-Neumann Algebras. The title is taken from a similar book by Arveson, where it's called An Invitation to C-star algebra, and Sundar has an invitation to one-Neumann algebras. This appeared in 1986, and again, rather than me say things about it, let's see what a reviewer has to say. So here is what the reviewer says. So it does not consist merely of theorems, definitions, and exercises. It is rich in informal remarks and explanations. The author displays good taste in deciding when to give no proof and when to give a complete proof, and is really an invitation for a quick visit, and it's definitely worthwhile to accept the invitation to obtain an insight into the modern theory of operator algebras. That's what the reviewer says about this book. Okay. Let's see. So this appeared in 86, around the same time, maybe a little bit earlier, in the mid 80s or early 80s actually. So there was a big news in the world of operator algebras, and this began with the work of Vaughan Jones. So what Vaughan Jones showed was the following. He was considering one-Neumann algebras and certain special kinds. So he began with these one-Neumann algebras called 2-1 factors. So a 2-1 factor is a very, very special kind of one-Neumann algebra, and no full stop there, so it's going to continue. Infinite dimensional with trivial center and admitting a trace. So what do these things mean? So infinite dimensional of course means it is sufficiently complicated. With trivial center again means that it's very far from being a commutative algebra. It is a highly non-commutative algebra. And admitting a trace. Admitting a trace is a very interesting condition. So we know that if you have regular small algebras, finite dimensional matrix algebras, they all admit traces, and in that sense it is similar to a matrix algebra. It admits a trace. He then defined a subfactor to be an inclusion of 2-1 factors. You take n, which is a 2-1 factor, and m, which is a 2-1 factor, and suppose that n is contained in m, such the whole data is called a subfactor. And associated to this notion of subfactor, he defined something he called an index, and this index is a measure of how large this subfactor is, in the sense of how many copies of n do you need to make m up. Roughly speaking, that is what is the index of a subfactor. So this is a certain number. Now when Von Neumann defined his algebras, one of the things that really interested him a lot was this phenomenon of continuous dimensionality. So normally when we think about dimensions, we think about 1-dimensional, 2-dimensional, 3-dimensional, and so on. But what does it mean to have something which is 1.5-dimensional or even worse, square root 2-dimensional? What are these objects? And in the theory of one-Neumann algebras, these occur in a very natural way. In particular, in the theory of 2-1 factors, this continuous dimensionality is really built into the whole theory. And this index is something that can vary continuously. So Vaughan Jones proved two very, very striking theorems. The first one is this. In 83, he showed that index is quantized. So what this means is the following. Index a priori can vary continuously. However, it only varies continuously in some part, and it doesn't vary, it has discrete values in another part. What he showed was the index cannot be an arbitrary number. It can take any value bigger than 4, but if it is less than 4, then it can be only certain very, very, very specific values. So this was his first remarkable theorem. And then he also showed that if you take a subfactor n in M, there is a way, which is now called the Jones basic construction, of producing an infinite chain of subfactors by repeating this construction which he calls the basic construction. Now that may not strike you as being a very remarkable theorem, but it did have extremely very interesting consequences. So while he constructed this infinite chain of the so-called tower of the basic construction, he also produced certain elements in these algebras, now called the Jones projections, and he used these Jones projections to construct a very famous invariant for knots, the Jones polynomial for knots. So that came out of this one-Neumann algebra theory initially. Now there are many constructions of the Jones polynomial for which you don't need any one-Neumann algebras, but it initially arose this way. Okay, so this is the work of Vaughan Jones in 83. Oh, I think this is wrong. This is, yeah, I think both are 83. Yeah, same paper, I think. Okay. Okay. So Sundar's, I think, first result in this area, sort of this area, dealing with subfactors and things is a paper, 1987 paper, in which he has a model for AF factors. AF is supposed to stand for approximately finite dimension. Sorry? Oh, AF, sorry, AF algebras, sorry. AF, yeah, model for AF algebras and Jones projections. It's a longer title. It's for AF algebras. In AF algebras is something called approximately finite dimension. It has a technical definition. Let's not get into that anyway, but I'll tell you what this paper roughly does. So here he begins with a pair of finite dimensional C-star algebras. Now these are, after moving around a lot in infinite dimensional, now finite dimensional will come as a real relief. So let n in M be finite dimensional C-star algebras, basically a direct sum of matrix algebras, familiar matrix algebras. Now the inclusion between them is known to be described by a finite and bipartite graph. Graph is just a collection of vertices and edges joining these vertices. And this graph is called the Brattley diagram for this inclusion n in M. So what this paper does is, there are several things that it does. So first, so he constructed a chain of finite dimensional algebras, n, m, m1, m2, so on, using paths in this graph. Now if you look at the Jones basic construction, this looks very similar, but there the n and the m that we had in the previous slide were huge infinite dimensional 1-dimensional algebras. Here these are very finite dimensional nice objects, and everything is determined by this graph, and from this graph he used paths on this graph to construct a whole tower of these finite dimensional algebras. Then he showed that if this graph satisfies some mild technical conditions, then the union of all these algebras admits only one trace. There is a unique trace on the union of all of these n, m, m1. Take the union of all of these, that is also an algebra. That algebra admits a unique trace. Then he also described in these algebras projections En, and these projections satisfied exactly the same relations as did the Jones projections in Jones theory. And remember that those relations were the basis for the Jones polynomial and invariants for knots. And then he also showed that the index corresponds to the Perrin-Frobenius eigenvalue. So index here, what does index refer to? Here these are just finite dimensional ones. The index was defined for 1-dimensional algebras. Here what index refers to is these algebraic relations have a parameter, and that parameter if you call the index, and that corresponds exactly to the Perrin-Frobenius eigenvalue of this graph. The Perrin-Frobenius eigenvalue is something that comes from a theorem of Perrin and Frobenius. It is the largest positive eigenvalue of adjacency matrix associated to this thing. Okay, so that is one paper of Sundar dealing with this model for AF algebras. Then in the early 90s, Sundar defined this concept that he called a hypergroup. So I'm not going to define it precisely. A hypergroup roughly is a set, and this set has a function, set G, let's say, G cross G cross G into these non-negative integers. And this function is denoted alpha beta gamma goes to alpha tensor beta gamma. Now why is it denoted in this peculiar fashion? Now normally functions are not denoted this way, but this is denoted in this fashion for a reason. The places where it arises, this kind of notation makes perfect sense. Satisfying 4 conditions. One is called local finiteness, one is called associativity, one is called identity, one is called contragradient. There are 4 things I intended to write down here, then I realized that there is no need to write down. It's enough to know that these are these 4 conditions. Now if you look at these conditions, they should remind you of course of a group, right, as also the name hypergroup. So you can think of a hypergroup as a group on drugs or something. It's hyper. So associativity, identity and contragradient roughly correspond to associativity, identity and the inverse operation in a group. Not just groups, the duals of compact groups also form a hypergroup. So there are 2 classes which are both covered by this definition of a hypergroup. What does this have to do with 1-dimensional algebras? So Sundar, this definition was made in order to prove the following theorem. So you take a 2-1 factor n, and then you take all these are a collection, I don't know what to say, isomorphism classes of bifinite irreducible NN bimodules. So these are certain objects that are associated with this 2-1 factor, and what Sundar showed was you can take these objects, you can sort of tensor them together, and out of various tensor decomposition rules, you can actually get a hypergroup in the sense of this definition. So this was one thing. And another thing, using the Perrin-Frobenius theorem, he showed that if a group if a hypergroup is finite, then it has a unique dimension function. There is a nice natural way to associate a positive real number to each one of its elements, satisfying natural conditions that you would want for when you would call something a dimension. Okay. Now, this theory of hypergroups was applied a little later. Okay. So, in order to explain how it was applied, I will have to say give you a few definitions. So, of course, we always would like to classify objects. So, now we have subfactors which we believe are interesting objects, and we would like to classify subfactors. Now, classifying subfactors, even if they are 2-1 subfactors and even if they are a finite index, is a really impossible thing. It's a very difficult problem, and we don't really expect that it will get solved in any meaningful way. But we can try, and if we cannot classify something, at least you can try and attach invariants. We would like to be able to distinguish two things at least. That is the minimum thing that you want to do before you classify something. And one such invariant for subfactor is a pair of graphs associated to n in M. There are two graphs called the principal graphs. Sometimes one is called the principal graph and the other is called the dual graph. In any case, there are two graphs that are associated to a subfactor. So, what Sundar showed with his student Vijayarajan in 93 is the following theorem. He showed that certain graphs, and these graphs arise a lot in Lie theory, in various places these Coxeter graphs arise. So, he showed that these Coxeter graphs, these families of Coxeter graphs, Bn plus 1, D2n plus 1 and E7 are not principal graphs. Well, actually it is not B2n plus 1, but a slight modification, but roughly we may think of it as B2n plus 1. So, these Coxeter graphs are not principal graphs of any subfactor at all. Independently, this was also shown by Masaki Izumi in 91 and Kawaigashi in 95. This is one, the technique to prove this theorem used his notion of hypergroups. Then with Uma Krishnan, another student in 96, he showed the following theorem, and this uses something called biunitary permutation matrices. We have already encountered permutation matrices. Biunitary permutation matrices are matrices which are permutation matrices which are unitary in two different senses. With two different ways they are unitary. And from a biunitary permutation matrix, it is possible to construct a subfactor. And for this subfactor, one would like to see when two of them are the same or when two of them are different, or at least distinguish them. And what they showed was that there are 18 equivalence classes of biunitary permutation matrices, and these are of size 9, 15 of which give subfactors where these graphs that I have talked about are finite, and 2 of them give subfactors with infinite graphs, and they left one out. They could not decide the status of one, but I think later that was also shown to be infinite, right? The 18th case. I think the last one was also shown to, the 3 of them are infinite, but they did this. Okay. So now let's now see what was going on. So this was in 93, 96. So now let's see what's going on in 97. So in 97, so Jones and Sundar wrote this book, Introduction to Subfactors. Now let me use their own words to say something about this book. So they say the aim of this book is to give an introduction to some of the beautiful ideas and results which have been developed since the inception of the theory of subfactors by such mathematicians as Adrian Ocneanu and Sorin Popa, and they succeeded to a very great extent in this. Now this book, most people who are working on subfactors will certainly have reason to use this book at one point or the other. For me, of course, it's a Bible, so whenever I have to refer to something, I refer to this book. It's a very small book, but it contains whatever is needed to deal with 2-1 subfactors and the so-called standard invariant in quite a bit of detail. Okay. Now, in the meantime, what was happening elsewhere? Now, that was not what was happening elsewhere. So this is from the Disney movie Tangled, and so it's the Rapunzel story. And as you can see, her hair, she's trying to untangle her hair with that hairbrush, right? So, and it's not really tangled. If you look closely, it looks very nice and neat. It's not really tangled. Okay. So the next thing that happened in the world of 2-1 subfactors was Vaughan Jones' invention of something that he called a planar algebra and something that he called planar tangles. Okay. Now this, according to Jones, is a planar tangle. A planar tangle consists of lots of data. There is one big outside circle, there are some inside circles, then there are some strings, these red ones which we call strings, and lots of additional data which I am not bothered to say. one way you can think of this tangle is something like this. You imagine that each one of these little ones, these little circles inside, are volcanoes, and then there's lava flowing down, out. This is an out, and you're looking at it from above. So these are raised, actually, these are above the plane of this, invented only in 99. So this theorem of Popa is 95, but essentially he proved that you can go the other way. But this going one way and the other way is not in any way a correspondence between planar algebras and subfactors, but it's just that you can go from one to the other and from this backwards. Sometimes whether you go this way and that way, or that way and this way, makes a difference typically. Okay, but let me point out what is the really nice thing about this theorem. What is really nice about this theorem is it takes its initial data is a 2-1 subfactor. This is a pair of 1-Neumann algebras with trivial center, contain one, contain the other, lots of these things, infinite dimensional, huge amount of data, and then it produces this very nice planar algebra. Planar algebra is a very nice object to deal with. The inputs that you put in here are all come from finite dimensional vector spaces. So it's just basically a collection of finite dimensional vector spaces and various operations you can do from them. Under good conditions, you can in fact recover the subfactor from the planar algebra. So this is a beautiful theorem. Okay, so Sundar together with me, I also started studying planar algebras at that time along with Sundar, and one approach to planar algebras was through generators and relations. Initially, when Vaughan Jones wrote his paper on planar algebras, the initial approach that was adopted was to define a planar algebra by something called generators and relations. This is a common approach when you do group theory or something like that. You study groups, you study some generators and then put in some relations and then study the group generated. Now, so what we showed along with Zeff Landau, we showed the following theorem. Associated to a finite dimensional Kac algebra H is a nice planar algebra PH with generators H in degree 2 and explicitly prescribed relations. So the existence of this planar algebra is not part of this theorem. Existence of the planar algebra follows from subfactor theory. Associated to this object called a finite dimensional Kac algebra is a subfactor, and associated to a subfactor, Jones has a planar algebra defined. So we know there is a planar algebra. But what we did in this paper was to take this planar algebra and remove subfactors from it. Essentially, we tried to describe this planar algebra without subfactors, just purely as a planar algebra. No subfactors, just generators and relations. Okay. Now, also in 2001, so Sundar wrote this book, and he's very generous about assigning credit. That's why my name appears there. Sundar gave a course on topological quantum field theories constructed from subfactors. I diligently took down the notes, and this book was the result. And so this explains the work in some sense of Okneanu and Turaev, Viro and all these things, applies it to construct from subfactors these objects called topological quantum field theories, which are of interest in physics as well. Now in this, much later in 2007, Sundar, Pati and I wrote this paper on another kind of TQFT that can be constructed from a subfactor. There is a very essential difference between the TQFTs discussed in this book and this kind of TQFT. The TQFTs discussed in this book are so-called 2 plus 1 dimensional. There are 3-dimensional topological quantum field theories, whereas these here are 2-dimensional topological quantum field theories. Now these we do not know, at least I do not know still. I've seen some approaches, but we do not know yet how to construct this from a planar algebra. If you are given a planar algebra associated to a subfactor, one doesn't know how to construct this topological quantum field theory. It really needs the subfactor. Whereas this one, what we did, we showed that you can construct a nice TQFT just given a planar algebra in a very natural way. Okay, that is about, yeah, so I should say that this generators and relations approach to planar algebra is often called a Skine theory for that planar algebra in question. These are of interest. Now let me come to the more recent. So that was 2007. I've come up to 2007. Now let me describe what's been going on in these last 5 years. Okay. So In 2007, Guionet, Jones and Shlyatenko gave a new and simple proof of Popper's theorem. So remember what Popper's theorem says. Popper's theorem says if you start with a planar algebra, then you can produce a subfactor for which it is the planar algebra. Essentially, that is what it says. And so Guionet, Jones, Shlyatenko gave a new and simple proof of Popper's theorem. What they did is they constructed a 2-1 subfactor whose planar algebra is P. Now the construction was simple in the sense it used only planar algebras, but the proof was not. The proof used techniques from lots of different areas. So it used free probability theory, theory of random matrices, type 3 factors. It used all kinds of machinery in order to prove the theorem, although the construction made no reference to all these things. And in fact, one of the stated goals of their paper was to connect all these areas together, and that's what they did. Now, so Sundar and I saw that this was a beautiful construction, but we couldn't understand their paper, so we tried to rework it in our own way, and we were somewhat successful. So what we showed was that this GJS construction, Guionet, Jones, Shlyatenko construction, has a purely planar algebraic proof. So you do not have to go out of planar algebras at all. You can completely stay within planar algebras and give a proof of this GJS theorem. In particular, you do not need free probability theory, you do not need random matrices, you don't need any of these things. You can completely give a self-contained proof for this thing. In fact, that illustrates the power of this Jones definition of planar algebra. There is so much that you can do just playing around with pictures. Basically, planar algebras only deals with pictures, and basically playing around with pictures you can achieve lots of things. This gives a proof of Popper's theorem. Now that was a major theorem, so you can just do that by playing around with pictures. That's what we showed. Now, although this was known, so after this was known, the natural question arises: if you start with a planar algebra P, then these n and m we know are 2-1 factors, but 2-1 factors are notoriously hard to classify as and they are of different kinds. Now we would like to know which 2-1 factors do you get from this GJS construction. What are the 2-1 factors that you get when you do the GJS construction to this planar algebra P? Yeah, so that's the question. What are the factors n and m that actually arise? So in 2009, at the end of 2009, so we wrote this paper which showed the following. So if P is the planar algebra of a Katz's algebra of dimension n, and that is the same planar algebra I was referring to earlier, then the factor m is the so-called interpolated free group factor LF 2 root n minus 1. So let me say a word about what this interpolated free group factor is. So as I said, planar algebras are defined by generators and relations, and this is similar to what happens in group theory. You have a group defined by generators and relations. If there are no relations, then we have the free group, the so-called free group. You can have a free group on 1 generator, or a free group on 2 generators, or 3, or how many ever generators you want. You can take a free group. And once you have a group, under some conditions, it gives you a factor. If the group is sufficiently nice, you get a factor. So in particular, you have factors like LF2 or LF3 or LF4. That is, you take a free group on 2, 3 or 4 generators and construct factors from it. Now here we have something called LF2 root n minus 1. So again, this phenomenon of continuous dimensionality. Now what does it mean for a group to have 2 root n minus 1 generators? Now we don't know what that means, but there is a sensible notion of what the associated one-Neumann algebra or factor is. That associated one-Neumann algebra is called LF2 root n minus 1. This is a definition due to Radulescu and Dykema. They showed that these free group factors exist, and what Sundar and I did was to show that in fact the GJS construction gives you a particular one. It is LF2 root n minus 1. Now this was quite satisfying, although it was almost just I think maybe a year later. A year later, Guionet, Jones and Shlyatenko showed the following, and we also showed this independently, but I mean we generalized it in one direction. This is the result that I have written here is a common intersection of the results. So we generalized in one direction, they generalized in another direction, but basically the theorem is that if you have a nice planar algebra of finite depth, that's another nice condition, then the factors that you get are interpolated free group factors of the kind that we already have. Okay. Let's see. Now this nice condition is often not satisfied by the planar algebras that arise in practice, and it's of interest to know what happens if this condition is not satisfied. That was we could not handle that problem, neither could GJS at that point, And recently, this is a student of Vaughan Jones, has shown that if you have something of infinite depth, then n and m are both LF infinity, that is a free group on infinite generators and the factor associated to a free group on infinite generators. Okay, basically this is what I want to say. So let me add a little personal remark rather than waiting for the felicitation function to do so. So I joined math science in '95, and that was just a few months after Sundar joined, and since then he has been a mentor to me, and I've learned lots of mathematics from him and lots of other things as well, for which I'm extremely grateful. So let me end with thank you, Sundar, and happy birthday.